Hey everybody! Today we are going to be practicing writing an equilibrium expression which is called Kc. So Kc, this is an equilibrium constant. Equilibrium constant. And really it's just a value that tells us in a reversible reaction, we have this little reaction like A plus B is reversible with C plus D, and these are just made up, obviously, they're not actual elements. This Kc value tells us whether it will move to the right or move to the left, which one's going to be favored once the reaction is done. That's why it's called equilibrium. Equilibrium is once the reaction's all complete and it kind of stops shifting around anymore. In a reversible reaction, and that's what this little symbol here means in the middle, instead of just a yield sign, that means that this chemical reaction could shift to the left, or it could shift to the right. Based on what Kc is, we can make a good educated guess. So if Kc is equal to 1, it's going to be perfectly balanced. It's going to be perfectly balanced. So we'll have equal amounts, we'll see how equal in a moment, of reactants and products. If Kc is between 0 and 1, we will get more reactants. So when this reaction's all complete and we're like, hooray, we've done this, you'll have more reactants. And if Kc is greater than 1, you'll get more products. You'll get more product. Okay. Here is what the equilibrium expression is going to look like. If you have a balanced chemical equation, we're going to start off with an easy one here, then our Kc value is going to equal. It's not the moles, it's going to be concentrations. So when we put these square brackets around a chemical, we are talking about concentration, moles per liters. We're going to put our products on top. The concentration that we have in C, the concentration of what we have of D, and it's going to be divided by our concentration of A multiplied by our concentration of B. This is a really simple one. We're just taking a look at this, getting started, understanding what the equilibrium constant is. So this is a ratio of our products to reactants. It's their concentrations. And this little equilibrium constant value, you have to be provided this equilibrium constant value, and it can change based on temperature and pressure. You have to be given it. It'll help you out in some later videos here. So let's take a scroll down, and we're going to try and increase the difficulty a little bit, because we like to do that. And yeah, I'm using all letters to get us started, but in a moment I'm going to do some actual real-world examples, and then hopefully this equation will make sense. So again, I have my little chemical equation here. It's a reversible reaction. That means it can go left or right, both ways, and we are going to write an equilibrium expression for this. When the chemicals have coefficients, the last time it was just AB and CD, this time it has little coefficients in front, Q, R, S, and T. And in a chemical expression, those could be 1s or 2s or 3s, whatever. You know how to balance chemical equations. Kc is still going to equal my concentration of my product C, but whatever this concentration is, it has to be raised to the power of its coefficient. In this case, S. And it's still multiplied by the concentration of the chemical D, but this concentration has to be raised to the power of its coefficient T. And we're going to all divide this, and hopefully you're starting to see the pattern, because on the bottom, we're still going to have the concentration of our chemical A, but it's raised to the power Q. And it's still going to be multiplied by the concentration of chemical B, but it is raised to the power R. And this is really the final equation for writing an equilibrium expression. You put the products multiplied on top, as long as it's their concentrations, and you raise each product's concentration to the power of its coefficient. On the bottom, we put the concentration of each reactant multiplied together, and each reactant is raised to the power of its coefficient. Now let's go and try a real-world example here. So we have 2 NO, it's gas, plus some oxygen, and it's gas, and it's in a reversible reaction. So it can go left or it can go right, and we'll do those calculations in a later video, what it's actually going to get. Today we're just practicing writing the equilibrium expression. And I've asked you, write an equilibrium expression for this equation right here. So you start off and you write Kc equals. You know that you have to start with the concentration of your products. In this case, we only have one product. It's NO2, so we put our NO2 in our square brackets. And remember, these square brackets mean concentration. We have to raise this to the power of a coefficient. In this case, the coefficient in front of the NO2 is 2, so we raise this to the power of 2. It's got to be squared. Divided by our first reactant, NO, so the concentration of NO. Does NO have a coefficient? It does! It's a 2, so we have to raise this to the power of 2. And we have another reactant, we have oxygen, and it's an O2. And then we check, does the O2 have a coefficient? Well, it's just a 1, so we don't have to do anything with it. And that's the equilibrium expression. Happy face, we're awesome. So let's move down, and we're going to do one more here, just to practice. So I'm going to scroll this up just a little bit to give us some space. And this time we're going to just ramp it up just a little bit, but I think that everyone's going to be fine. So we're going to write another equilibrium equation. We got some oxygen, that's a 5 O2s, not a 50, and it's a reversible reaction with 4 nitrogen monoxide plus 6 waters. So once again, we have a balanced chemical equation, and you've been asked to write a Kc value. So our Kc equation is going to be the concentration of our products. Our first one is NO. Does the NO have a coefficient? It does. It's a 4, so we raise this to the power of 4. Our next product is water, H2O. We write that down. Does the water have a coefficient? It does have a coefficient. It's a 6, so we write a 6 right here, and we put this all over. We're going to do our reactants. So in the bottom, we have our first reactant, which is NH3, ammonia. Does the ammonia, the NH3, have a coefficient? It does. It's a 4. And to finish this off, our final reactant is the oxygen, that O2. Does the O2 have a coefficient? Yeah, it's that little annoying 5 that made this look like a 50. And we're going to put that 5 right there. And again, that is a successful equilibrium equation. Great job. Hopefully this was helpful. Thank you very much.